So I'll post this in a little bit for my other classes because this was definitely something that people wanted a little bit more help with. And so I thought seeing today's class would help. I can't do this all the time, but I think definitely for this one, it is important. So continue. Okay. So what I'm going to do now is, let me go day one. Okay. I am not going to hand you out the printout today because I'm going to go for a simplified version of the printout. So just get some paper out. If you need to borrow some paper, let me know. There's paper up here on my thing, or you can borrow paper from somebody else. Cool? Because I'm doing the simplified version. So the first thing I want to talk about is let's think about dropping a ball. And my question is, if I drop a ball from a building, so for some reason, I don't know why I'm doing it. For some reason, I'm doing it. I stand on top of the building, drop the ball, and it falls. At 0 seconds, at that instant when I let it go, it's not going fast at all. Do you agree? At that one instant, it's hanging in midair. And then after 1 second, it goes faster. After 2 seconds, it does whatever it does. My question is, if I stop the clock at t equals 1 second, at that instant, what is its velocity right then at that instant? Okay? Does that make sense? Now, even if you may know it from physics, we need to talk about some of the math behind what's doing what it's doing. And also so that we can talk about change in other ways. So here's the way we think about it. I don't know how to talk about change in an instant because we haven't talked about that yet. So what I'm going to do is think about it in change over time. I could go from 1 to 2 seconds. How fast is it going? From 1 to 3 seconds. Whatever, right? But here's how I'm going to think about it. I'm just going to say from the time 1 to 1 plus h, where h is something really small. H is small. H is, bless you, very, very, very small. Very small, and it's positive. Okay? Does that make sense? And I can talk about its average rate of change on that very small interval. So if I want to talk about how things are changing, here's what I'm going to do. I'm going to talk about how is S changed, right? So what would be, first off, how is my position changed? Well, my first position was at time 1, and my second position was at time 1 plus a little bit. Does everybody agree that that's how far I've gone? How far were you at 1? How far were you at 1 plus a little bit? That's how far you've gone. Yes? Yeah. Okay. So let's see what that is. Well, if this is S, what would S of 1 be? Don't overthink it. 4.9 times 1 squared, which is 4.9. So this is just 4.9. Let me delete. So this is just 4.9. Can I replace that? Is that okay? And then if I do S of 1 plus a little bit, don't overthink it. Don't overthink it. What does it mean to be S at 1 plus a little bit? Very good. Thank you. Owe you $1. So what does that mean? It's 4.9 times, what does 1 plus h squared equal to? How do I find that? Very good. I take 1 plus h times 1 plus h. And so it'd be 1 plus 2h plus h squared. Very good. Is that okay? This says very small and positive. So h is very small and positive, right? Okay. So what did we just find? Oh, poop. Let me go back. We just found out that just that one. we just found out that this stuff right here, can I make it a lighter pink? Custom, a lighter pink. So that this thing right here in pink is equal to just this stuff. Do you agree? So I can replace it. Take all this, move it over. And so in here is going to be 4.9 times 1 plus 2h, bless you, plus h squared, but then minus that 4.9. That's our distance. If we say, where were you at 1 and where were you at 1 plus a little bit, the distance you've traveled is that. Is that okay? Yeah? Sahara's okay with that? Okay, just make sure it makes sense. Okay, now, do you agree how do I want to do this? If I wanted to, how do I want to do this? Yeah, do you agree that I could pull out a 4.9 if I wanted to? Yes, from those two terms. I'd be left with 1 plus 2h plus h squared minus 1. Is that okay? Can I do that and everybody won't be mad at me? It's okay? Well, what's great about that? What happens nicely? Ones cancel out and you get 2h plus h squared. So my change in s, how is your distance changed from 1 second to 1 second plus a little bit? Is that. That's how far I've gone. Is that okay? But what I'm really interested in is how things have changed over time. And I literally put it over time. Yeah, go ahead. What's your question? Yeah. So all we did was we said that this turned out to be that, right? Okay. Well, now watch what we can do. Now I want the average velocity over time. So if I talk about the average velocity over time, that's going to be from 1 plus h minus s of 1, but I'm going to divide it by how much time has changed. Well, I went from 1 to 1 plus h, so how much time has gone by? Very good. We stop and just enjoy the fact that you got that. Good job. H is how much time has gone. So it's s over 1 plus h minus 1 over h is my average rate of change, how things have changed on average. My average velocity. Is that okay? Yeah? Well, I think we just did a little bit of work a second ago. We said, look, our average velocity, what did we find out that this top thing was equal to? 4.9 times 2h plus h squared, right? All over h. But in the very beginning, they didn't say, how are things changing over time? They said, how are things changing at 1? Right? So let's think about how it's changing over time. And so for the people playing along at home, to make my life easier, I'm going to, give me just 1 second. I'm going to do this and do this. I'm going to take a picture of the board so they can see what we're doing. Kablamo. Okay. Use this photo. So the first thing I'm going to say is, do you agree that I can factor out an h and cancel it out? Is that okay? So I'm going to cancel out an h because I'm going to do 4.9h times 2 plus h all over h, and those cancel out. So it turns out that my average rate of change is really just this. Is that okay? Make sure and prayer. Can I cut it? Cut. Is that okay for my average rate of change? Yes? Yes. No, I could put parentheses. Yeah, I was just being ridiculous. So now check this out. So what could I do? I wanted to know what was happening at exactly 1. Oh, you want me to go back? Here you go. I can go back for a second. Do you? Okay, cool. So here's my average rate of change on the interval from 1, let me use my red, from 1 to 1 plus a little bit. That's what it is, right? So if I want to go, bless you, if h was equal to 0.1, I would go from 1 to 1.1. Do you agree? And that means this would be 2 plus, and I would put 0.1 in here. Well, if you do that on your calculator, it turns out that turns out to be approximately, bless somebody, turns out to be approximately, why is it being mean to me? 10.29. But what if I went from 1 to 1.01? So a very small interval, 1/100th. And I ask, what is the average velocity? Well, that'd be 4.9 times. Well, now in for h, my interval is 0.01 long. So that means that this h turns out to be 0.01. And it turns out that over that very small interval, my average velocity is 9.85. And I let the interval get smaller to tens, hundredths, 1/1000th of a second. My average velocity was 9.8. Tens, hundreds, thousandths, 10,000th. 1/10,000th of a second. My average velocity is still 9.8. So what do you guess the function wants to be when h is 0? 9.8. That's how fast it's going, is 9.8. But I can't plug, but I'll just say that's what it wants to be. Do you agree? That's the limiting value. And we've talked about limits before. But let's go back. Is it clear why in the very beginning we didn't put 0 in for h? Because you can't divide by 0, right? Because it makes no sense to talk about the average velocity over an interval of length 0. But that's actually what you're doing when you look at the speedometer of your car. It's saying you're going 65 miles an hour right now, not over an interval, at this instant, over an interval of 0. So your car is actually taking limits all the time. Yes?
You change the form of it. Can you plug in 0 or no?
Good. What did we do? We said that this was the average velocity. And what did we do when we changed that form? We got rid of the hole. We got rid of the hole at 0. So anytime you're thinking about velocity at a point, there's a hole at 0, and it makes no sense. So you have to do a little bit of math work to remove the hole, and then you can talk about an interval of 0 length. That's what it means to be the instantaneous velocity. In other words, the speedometer on your car is talking about how fast you're going right now, an interval of length 0. Does that make sense? There you go. And so now what I'll do is I will never show another way to talk about it because that can be confusing. So so we did all that, and that's beautiful, and that's beautiful. So here's really what we did. Oh, and this is so pretty. The instantaneous velocity at time 1. You just take your average velocity from 1 to 1 plus a little, but you let that plus a little go to 0. That's why we had to talk about limits before today, because we wanted to talk about change, because calculus is all about change, but I wanted to talk about change at an instant. But that actually makes no sense and will make your head explode. So we just talk about it over a very small interval and say, well, what does it want to be if that interval went to 0? And that's it. So that's why we take this average velocity and we take its limit as h goes to 0. And we call that the derivative at 1. The derivative is how is it changing at 1. The derivative at 2 would be how is it changing at 2. So it's the instantaneous change. Not over an interval, but at an instant. Pretty cool, yeah? Like if you were sick and we could tell that your temperature changed over the last hour, it went up 5 degrees, and you're now over 100. Well, at some point, I could have stopped time and found out the instantaneous velocity of change. That like at this second, it was changing at a rate of like 1 degree per hour at this exact time, right? Because you're pretty sick. That's what we're talking about when we talk about these things, these derivatives, which we'll call it. All right. So here's really what the picture will look like. And this is the only way we're going to talk about it. This is the average rate of change. On the interval from A to A plus H. It's how are things changing over an interval. That's what this is. You may have heard it called before the difference quotient because it's got subtraction and division in it. It's a difference quotient. That's why you may have played with it before. So difference quotient is just the slope of the secant line or the average rate of change. So we're saying if I go from A to A plus a little bit, how is this graph changing? Well, I could just draw a line between them and tell you how that changes. That's what it is. The slope of this line is the average rate of change. And it describes overall, well, if I just replaced our graph with a line, that's how it's changing. So we call this orange line the secant line. And the secant line is just a line between 2 points. And I gave it a name because there'll be a different type of line in a second. So let's see if we can't see this fraction inside this picture. Well, if that's just the slope of the line, if I look right here, what's the difference between these two y values? Well, this one is f at a plus a little, and this one down here is f at a. So the change in y is f at a plus a little minus f of a. But then if I walk from a to a plus h, how far have I gone? H. So now do you see the rise over the run in this thing? Yes? Thank you. What are your questions? Are we okay so far? Pretty good, yeah? Happy Friday, by the way. Okay. So here's the big difference. This is the whole calculus 1. Everything that's on the board is all of calculus 1. This is the slope of the secant line between 2 points is the average rate of change. This is the slope of the tangent line. It's called the instantaneous. And I said it like that so I could spell it. The instantaneous rate of change. How are things changing at this instant? What did I have to add to the average rate of change to make it the change at an instant? What math thing did I have to introduce? The what? The limit. So this is how things are changing on average. This is how things are changing on average, but as soon as you add the limit, it's how are things changing at a point. Because I let the length of my interval h go to 0. Okay, I'll plug you up. All right. Yeah. You okay? You okay, yeah?
Oh, yeah.
You sure? Okay, let me know what's up. Yes.
So it's just the limit is what makes it at an instant.
Yes. The limit is the key thing. So when we're looking at this picture, what happens is instead of the secant line here, if h is really small, then maybe it's a plus a really tiny h, and we're just talking about this secant line. And then as h gets smaller, it's this secant line. But what it's trying to get to is where h is 0, which would be the tangent line where you touch at only 1 point. And that tells me how the curve is changing at that moment, is if we were out on the tangent line. That's how it's changing at that moment. Pretty cool? Yes?
So then, like, when you take, like, the actual, like, derivative of the function, is that just, like, an infinite amount of those tangent lines?
Oh, good. Yeah, it's finding the one tangent line. It's letting the secant line become the tangent line. Okay. Yes. And what that function gives you is you can now tell me any point, any time, and I can tell you exactly how it's changing. That's what the derivative function is it tells you at any point how are things changing at exactly that point. That's what we'll do. Great question.
On the triangle you drew, what was the vertical line? Was it f of a plus h?
Yes.
Minus f of
Right? Is that cool? Yeah. Yeah. Keep on asking me questions and make me re-say it because that's how you're going to understand this. Is just saying, can you say it a different way? But the great thing is, this is a lot like looking under the hood in NASCAR. You're like, ooh, that's scary. Very soon, we're going to shut the hood and just drive fast and go left and go left. That's what we're going to do. So that's where we use these limits to make the car, which are derivative rules, which are going to allow you to do stuff fast, as opposed to getting your hands dirty. But we have to have these first introductory ideas before we can get that. So here you go. Let's change this a little bit to, let's just find the slope. That's all I want. Find the slope of the line that is tangent to x squared at the point 3. So here's the point 3. They want to know, how is this graph changing exactly at that point? So I'm going to have to pull it up. Oh, poop. Don't be mean. Boom. Oh, man. It doesn't look like it's hitting it at one point. Can you see in your mind that it's hitting it at just one point? Is that okay? Because I can't draw. Okay. Here's the idea. The way to think about how the curve is changing at a point is imagine you're driving on this curve on an icy road. Dun, 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 dun. Everything's fine. No, no, no. Oh, no, we're going to die. And it goes this way, and you shoot off in this direction. So the way to think about it is we just continue in the way that the curve was changing at that point. That's what the tangent line would be. Does that kind of make sense? But we're all okay because this is just a field and we're okay. So we're going around here, hit a patch of ice and keep on going. You've gone off on a tangent. Yes, which I do quite often. Gone off on a tangent. Okay. Okay. Now, I don't know how to deal with things on a point, but I do know how to deal with them over an interval. So I'm going to say, let's go from 3 to 3 plus h, and I'm going to talk about that secant line. Right? So what is the slope of that secant line? It's f of what minus f of what? 3. Backwards. F of 3 plus h minus f of 3. Right? It's always going to be that way. I can see how you could easily mess it up. That's the change in f, right? What is the change in h? I mean, the change in x. It's h, right? Do you agree? But this is the average rate of change. This is the average rate of change on the interval from 3 to 3 plus h, right? But that's not what we want. What do we want to do? Do what? We want to find out how things are changing at an instant. So we want to take the limit as what happens. Very good, as h goes to 0. Oh, yeah. Hello. Yes. Yes. Okay. Yeah, Mom was wanting to check on you.
Oh, yeah.
Yeah. Yeah, she said she's good. Thank you so much. Yes, ma'am. Fine. Awesome. Cool. So does that make sense? Yes? So now all you have to do is just be careful with the algebra. So on your iPad, if you could resize it and make it super small, now you have tons of room. Oh, yeah, you don't have an iPad. Okay, so here's what I would recommend doing. I would say on your scratch paper, let's first do the easy one. What does it mean to be f of 3 if your function is x squared? 9. You just take 3 squared, which is 9. So that means this is just 9. Is that okay? Then on your scratch paper, you say, what does it mean to be f of 3 plus h? And so what do? 3 plus h squared, yes? Which is 9 plus what? 6h plus h squared. So all of this is just that. Subtract all over h, and it's the limit as h goes to 0. Is that okay? Yeah. What is wonderful? Now, here's a really interesting thing to think. We just took something I don't know how to do, the slope of a tangent line, and turned it into something I do know how to do, a limit. You're going to do that over and over again in math. Just take something you don't know how to do, turn it into something you do know how to do. What happens nicely? Nines cancel out, and you get this limit. So it's a brand new limit. What do you always try first? Plug it in, and what happens? Which means there's a hole. Where's the hole at? 0. So you factor out your h. Oh, but don't drop your limit. So don't forget your limit. So h goes to 0. But what is great about h over h? That's equal to 1. So really, the limit as h goes to 0 of 6 plus h. So we simplified down our average rate of change, and we found out that the slope of our secant line turned out to be 6 plus h. But I don't want the secant line, I want the tangent line. So I actually take the limit and let h slide to 0. And what does the function want to be at an instant? 6. That's what the slope of the tangent line is, 6. And that's it. Pretty cool. Yeah, and for those of you watching this, especially people in other periods, I just shot myself in the foot trying to show us too many different ways to look at it. I think we're only going to stick with this one definition because I think it's just going to help us focus better. So that will allow us to do something like this. Well, actually, before we go any further, what are your questions on this? Yes?
Can you go back to one slide just for 2 seconds?
Yes.
For the answer, do you just write 6?
Yep.
Okay.
Because really what it turns out, it's just turned into a limit question. Yes. So it's just a limit question. Yeah. Is that cool? So let's look here. Now I've got the function 1 over x. Draw what 1 over x looks like on your paper. Do you remember what it looks like? Again, this is why I had you memorize these things. So hopefully it helps when you see them and it has more meaning. It looks something like this, yes? So they want to know at x is equal to 2, which is going to be somewhere over here, what is the equation of the tangent line? We'll do that in a minute. Just know that first it wants the slope of the tangent line. So we'll do slope and then come back and get equations so you don't freak out. Is the slope of the tangent line going to be positive or negative? Negative. So just by having memorized what the equation looks like graphically, I already know that my answer should be negative. That's why I had you memorize stuff, yes? Okay. So I know that the slope of the tangent line is just going to be related to the slope of the secant line from 2 to what point? 2 plus a little bit. In math, h just means a little bit. So what is the numerator going to be in my difference quotient? F of 2 plus h, f of 2 over h. This represents what in terms of my picture? This is the slope of the what? It is the average rate of change. Very good. For the slope of the secant line between 2 points. But I want to find the slope of the tangent line. How do I turn a secant into a tangent? The limit as the length of your interval goes to 0. H goes to 0. And that is it, folks. boop, boop, resize, boop. Okay. Now, over here on my scratch paper, I'm going to say, look, I can do f of 2. What is f of 2 if f is 1/2? 1/2. Dun, 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 dun. That's good, even for a Friday. I know what I'm doing. Now, what does it mean to be f of 2 plus h? Very good. 1 over 2 plus h. So really, it's the limit as h goes to 0 of 1 over 2 plus h minus 1 over 2. There's that. There's that one. There you go. So it just turns into an interesting limit question. Okay. Do you have any hint for what I should do to do this one? What do you think, Olivia? Yep.
Well, like, don't you multiply both by like 2 times 2 plus 6?
Rock star. What do you call it if I multiply the top and bottom by 2 plus h? Very good. You both said it. Well chosen one. Because it's a good choice, yes? It doesn't matter if you remember the name. It's just kind of cute. Not a lot of people know that name. I just read it in the textbook once and think it's a great idea. It's a great way to call it. So, what does that mean? What happens when this hits that? What are you left with? 2 minus, then hits this. Make sure you have parentheses 2 plus h. Do you see how that would screw things up if you didn't have those parentheses? Yeah, let me stop for a second. Talk to me. Does it make sense? Or do you want me to say it a different way? I can say it a different way if I need to. Do you want me to? Talk to me, Sturgis. Can we say it a different way?
Sure.
Yes. Okay. So the intermediate step that I left out would be, I'm going to take all this, give myself some more room and go boop, 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 boop. I'm going to hit resize and go. Okay. The intermediate step I left out, and that's usually where the weirdness comes from, is going to be a 1 over 2 plus h is going to get hit with this thing outside to 2 plus h. And then the minus 1/2 is going to get hit with that 2 plus h all over that h to 2 plus h. So what that does for us is these cancel out and leave the 2. Boop, boop. And these cancel out and leave the 2 plus h. Does that help?
Yeah, so that's why you keep the parentheses.
Yes, that's why you keep the parentheses. Because you want to subtract all of this. Because if you don't put them there, you're only taking away the 2. But you need to take away the 2 and the h. Good question. So why is that great? Because what happens? 2's cancel, and you're left with negative h. Because remember that negative distributes over 2h, 2 plus h. We're almost there. So it's a new limit. What do you always try? You get h over h, which means there's a hole, which we always expect in these type of problems. So what do? Very good. Like I said, factor out, not just cross out. So you actually do this thing. That's just equal to 1, so it goes bye-bye. What you really have is the limit as h goes to 0 of negative 1 over 2 plus h. As h slides to 0, that equals? Negative 1/4. That is the slope of the tangent line at that point. Is that okay? Yeah. Yeah, the other was just too rough. I think it was, yeah, it was just weird. Is that okay? Okay. So that means the slope of this tangent line at the point 2 is equal to negative 1/4. That's what we're saying. That's how the function is changing at that point. It's saying that for every 4 steps you take forward, you go down 1. That's how it's changing at that instant. Does that make sense? Okay. Let's do one more. I haven't done this with any class today.
Wait, was that the equation? Yeah.
Oh, good. No, good call. Let's go back and do the equation of a line. Sorry. So it's all sitting there for us. Let's do the equation of a line. So anytime in this class somebody asks you to do the equation of a line, you're going to write down the slope-intercept form. It is the most important version of a line. Y minus y1 is equal to mx minus x1. That is the most important version of a line. And it turns out in calculus, oftentimes we just approximate curves as long as they're nice enough, and we'll talk about what that looks like, with a line. And that's fine. So I can talk about this thing, oh poop. So this is our curve, 1 over x. Right here at x is equal to 2, I want to find the equation of this line. Well, you already know what the slope is. What did you say was the slope of that line? Negative 1/4, right? Right? And then you already know one x coordinate on that green line. What is one x coordinate on that line? 2. What is the y coordinate associated with 2 on this line? 1/2. Because if you're on this line, you're also on this curve. So that's the equation of the tangent line to the curve. And you can leave it just like that. Do one more example and then we will be done. Yes?
Like, if we were to ask just to find the equation, we'd have to find the slope, like do all the things on the slope first. Okay.
Yep. Very good. Because if we just knew the function and the point, we would know everything but that. And this is the tangent line at a point. And so what we would say is, we would say that the derivative at 2 is equal to negative 1/4. That's how we write the slope of the tangent line, is we say the derivative at that point. Yes? Yes, yes. Because we knew that the tangent line was also where it hits. It also hits my curve. So I just plugged in x equal to 2. And right here, I got a height of 1/2. And that's not only on this, but also on my line. So that means 1 point on my line is 2 1/2. Just happens that it's also a point on my curve because it's the tangent point. Great question.
So we can just leave the equation that one.
That is not a ditch I'm willing to die in. Yes. Pretty cool? Let's do one more, and then we'll be done. So let's find the slope of the tangent line to this curve at 4. First, draw what that curve looks like. What does the square root of x curve look like? Yep. So if you say at 4, what does the tangent line look like? Do I expect my answer to be positive or negative? Positive. Let's see what it is. Well, I'm going to talk about from 4 to 4 plus a little bit. And I'm going to find that secant line. And then I'm going to let that secant line, the width of that interval, get smaller and smaller until it becomes the tangent line, yes? So I'm going to do the limit. Well, first, what's the secant line? If I go from 4 to 4 plus a little bit, what is it? F of minus divided by. This is what? What does this represent visually? Very good. The average rate of change, slope of the secant line. Very good. So then I take the limit as h goes to 0, and all of this represents instantaneous rate of change, or the slope of the tangent line, like Caden said. Good job. Make sense? Okay. And yes, you write it down like that before you start plugging stuff in because you're doing slow work. I'm going to ask you to do less but better. So I'm going to take all of this. I wonder if it'll let me get that. Resize it. Oh, well. All right. Oh, it left some of it up there. That's okay. 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 So I come over here. I say, look, here's my scratch work. I'm going to say f of 4. What's f of 4? 2. Why isn't it plus or minus 2? Because it's just 2. The only time you do plus or minus is when you're solving an equation and you worry about if there are 2 answers. For the function 4, it only gets out one output, a height of 2. That's why there's not 2 answers. So that means that this is just 2 minus, what does it mean to be f of 4 plus h? How do I find f of 4 plus h? Take the square root of 4 plus h. Square root 4 plus h. Right? So that's my change in y. What is my change in x? It's just h. I take the limit as h goes to 0. So the height, we just said that my height was the square root of 4 plus h. I'm at 4 plus h. And my height at 4 is 2. So the change in y is this, and that's the change in x. Is that okay? I took something I didn't know how to do, slope of a tangent line, and turned it into something you do know how to do. Just a limit. What jumps out at you? What should punch you in the face? The square root. What is it? A real big hint to use? What tool? A well-chosen one. What specific well-chosen one? Square root of 4 plus h plus 2. What do we call that? That's the conjugate of that. So I take that conjugate and I put it on the bottom again. And now that whole thing is a well-chosen one. Great work. So now I take all this and do resize. And I'm going to move it over here. Take all this. Oh, I wonder if that's going to take that too. No. Resize. Make it really small. Boop, boop. Okay. So what do I get on top? The limit as h goes to 0 of what? 4 plus h minus 4 all over h root 4 plus h plus 2. Boop, 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 boop. I know I'm on the right track, right? Because what happens nicely? 4's cancel out, so you get h over h 4 plus h under a root plus 2. Well, what can you do now? What about the h? Good. Factor it out. You get 1 over root 4 plus h plus 2. But h over h is just 1. Always is. Unless you're at 0, but we don't care about 0. So now I just let h slide to 0 if I have root 4 plus h plus 2. Do you see if h is 0, I just have the square root of 4, which is? Square root of 4, which is 2. So it's just 1/4. So that means the slope of the tangent line is 1/4. Yes.
Would you want to write it like the
No, that's not the most important. I'm just making sure we see the connection. Great question. Great question. So now, just to follow it up, they said slope, but if I wanted to do the equation of the tangent line, well, what do I write down for the equation of the tangent line, just to practice? Y minus y1 is equal to m. And it turns out that if you've done all this work, it all should be there. What is the slope of the tangent line? 1/4 at what x value? Very good. At 4, that's where we're looking. And what is the associated y that we found when we were doing our work? 2. So it's all there. Do you see that it's all in there and you really don't have to do anything? And you're done. And that is today's lesson. Hopefully a better version. Peace out. Have a great day.